an electronic distance measurement. The topics covered in this video include the major random errors in EDM observations and an example calculation for random error estimation in a distance measurement. The major random errors encountered in EDM measurement are four. First, miscentering error of the EDM instrument over the station. This is a setup error that the instrument operator will have setting up over the point. This error is typically anywhere from 1 to 4 or 5 millimeters, depending on the skill of the instrument operator. The second error is the miscentering error of the reflector or the prism over the station. If we have a rigid setup here, which is not illustrated in this sketch, then that error would probably be very similar to the miscentering error of the EDM instrument. However, in the sketch, we're showing a prism pole, and prism poles with the bubble sensitivity given on a prism pole are somewhat difficult to hold over the forward point. The third error is the EDM instrument constant miscentering error. That is internal to the EDM instrument itself. And so this is where the wave generator is slightly off the geometric center of the EDMI instrument. And manufacturer specified values are anywhere from 2 to 5 millimeters in magnitude. The fourth error is the EDM instrument scalar error in the measured distance. This is the uncertainty in the wavelength of the electromagnetic wave that's sent to the prism and returned. So it's just an uncertainty, and it's typically specified as so many parts error in a million parts measured. Let's look at the equation used to estimate the random error in an EDM measurement. First of all, the equation has four parts. The distance measured has an E sub I, E sub R, E sub C, and a ppm times d. Each one of these terms can be defined as E sub d is the error in the observed distance, millimeters or feet. E sub I is the estimated miscentering error of the instrument over the station, so that's the skill of the instrument operator. E sub R is the estimated miscentering error of the reflector over the forward station. Again, that would be the skill of the prism pole handler. And E sub C is the manufacturer specified miscentering error for the EDM. And we can see in it as an example here, one manufacturer would specify possibly that there's 3 millimeters of constant error, centering error, and there's 5 parts per million error in the distance measured. So the ppm error is this manufacturer specified scalar error for the EDM, and that is the 5 parts per million as illustrated in the previous line. D is nothing more than the recorded slope measurement in the EDMI process. So let's take a look at all 4 of these errors and see if we can do something with an example problem. Here's our example problem description. An EDM instrument has a manufacturer specified accuracy of plus or minus 3 millimeters plus 5 parts per million. It's used to make a slope observation equal to 1,347.290 meters. The instrument person estimates that she can set the total station over a point within the limits of 2 millimeters. The rod person estimates that he can hold the prism pole over the station within the limits of about 6 millimeters. From this information, then, determine the estimated random error in the measurement. So we will rely on the equation just given previously, where E sub d is the sum of the squares of the 4 errors encountered in the measurement. Let's compute the ppm times d error. First, the ppm times d error is 5 parts per million error times the distance measured. We're going to convert that to millimeters because everything is going to be in millimeters here. So this is 1,347,290 millimeters. That's equal to our distance of 1347.20 meters. If we make that calculation, the result turns out to be 6.7 millimeters. So now all we need to do is plug in the remaining values and solve for E sub d. E sub I is 2. E sub R is the 6 millimeters of the rod person. E sub C is manufacturer specified of 3. And then the ppm times d we have computed to be 6.7. So just take the square of all these quantities and sum them up, and then take the square root of the sum, and we will get our result. And our result says that we have about 9.7 millimeters of error. This is random error in 1,347.290 meters measured. That is a very small amount of error for such a large line. What would the precision be here for this particular line? Well, we can compute that. Precision is the error divided by the distance measured. So it's 9.7 millimeters divided by 1,347,290 millimeters, or it's about 1 part error in 139,000 parts measured. So that's a very precise line, even with an instrument that doesn't have the greatest accuracy specs. Some instruments, most instruments today, are 2 millimeters plus 2 or 3 parts per million. In summary, in this video, we have looked at the following topics. We've looked at the major random errors in EDM observations, and we've looked at an example calculation for random error estimation. The outcomes, what we hope you learned from this video, include your ability to recognize random errors in EDM observations and the ability to estimate the size of random errors in EDM observations. This ends the video lesson.